Let's see how do we represent loops in assembly code. In this example, for the pseudocode here, we have a equal to 0. We assign the value 0 to a. Then repeat these statements, these two statements. Output star, then increment a by 1 until a equals to 5. So we get out of the loop if a is equal to 5. In the assembly code, we can break it down into these statements. LDM directly 0, stored 0 into the accumulator, then store that value in the symbolic address A in the memory. Here we have a label called loop. In this loop we have LDM 42. That means we entered the loop here using that statement. The first statement in the loop, this is an indication of the start of the loop. We have output star. How do we output star? That means we have to get the value, the decimal value of star from the ASCII table and store it inside the accumulator. And the ASCII value, the ASCII decimal value of star is 42. Then store this one into the accumulator, then output the equivalent character, which is star, on the screen. Then we have to increment a by 1, so we have to load a into the accumulator, the value of a, and increment it by 1. Then we store that value into a. That means we update the value stored in that symbolic address of a. So we update a with the new value. Then compare that value, which is a, with 5. We're going to compare the value of the accumulator inside the accumulator with the value 5. So if it's not equal, we go back for the loop. If it's not equal, we go back for repeat. Here, if it's not equal, we go back for the label loop, and these statements would be executed again and again till a is equal to 5. So if it's equal to 5, this is now going to be executed. Let's see how do we perform the input and output process in assembly code. Let's suppose that we have this line of code, input A in pseudocode. That means we ask the user to input values and store it in one of the variables called A. In assembly language, we can say N, so we receive one of the characters from the keyboard and store it in the accumulator. Then we store whatever in the accumulator, the ASCII value for that character, into symbolic address A. In the second example here, we have output B. That means we're going to output sequence of characters. We output a string, which is a sequence of characters on the screen, like output a message. In assembly language, how do we do this? We can load -1 into the indexed register, the index register. We load -1. Then starting from here, we're going to repeat these steps. That's why we have a label loop. So increment to the index value, the index register value. That means we are going to add 1 to the -1 to become 0. So we start from 0. And this one is indexed addressing. That means load whatever in that symbolic address plus, and go to that address, like if b is equal to 100, which is the address in the memory. So go to that address and add the value of index, which is now 0, to that address to calculate the new address, because this is indexed addressing. The indexed addressing, as you know, is calculated from the address given and whatever the value in the index register. So we add this value from the index register to that address, which we suppose now to be 100. So it's 0 plus 100, that means 100. Go to that address and get the value stored and store it into the accumulator. Then output the corresponding character from that value stored into the accumulator. Corresponding character would be displayed. Uh, then compare the value stored in the accumulator with 13, the value of 13, which is actually called the carriage uh, return. Uh, this is a kind of indicating that we reached the end of the line of text. And this option is used in both the printers to know how to indicate that we reached the end of the line, and used also in the old typewriters to know that we reached the end of the text. So we are ready to start a new line of text. Okay, so this is kind of indicator only that we reach at the end of the string in that case. So if we reach at the end of the string, uh, we end the loop. If we didn't, that means we still have some character, which means we still have some characters to be displayed on the screen. So we jump to the loop to add one to the index, which is now which is going to become one in that case, because we assume that index was 0 in the previous step. So now it's 1. Then we add 1 to the address B to go to that address, the new address, and we suppose that B was 100. That means now the new address is 101. So go to 101, get the value, and consider it the ASCII value for the character and store it into the accumulator. Then we output the corresponding character for that value, the ASCII value, on the screen. Then again we compare did we reach the end of the line or not. If not, we go again and get the next character and so on till we reach the end of the string. Um, okay, if we move on to the third, if we move on to the third example here, input A. Here, the difference between this one and the upper one is that for the upper one, we assume that we input only one character. But here, assume that we input a sequence of characters, a string, like your name or a message. So how can we do this using assembly code? First of all, we load again -1 value into the indexed register. Then we increment, starting from here, we have a loop again. So we increment the index to become 0 because it's already having the -1. So if we add 1, that means we start from location 0, or index register will contain 0. Then n, we ask the user to input a character. This character ASCII value is going to be stored into the accumulator. Then we store here, this one is called stx, not sto. In sto, we know, like this one here example, we know that sto take that value from the accumulator and store it into symbolic address A. But stx, if you return back to the table of this opcode meaning, it means take that value from the accumulator and store it store this one into the new location, which is location A, address A, plus the value stored in index register. So if index register is 0 and that location is 100, so go to 100 plus 0, which is 100, and store the value that have been stored into the accumulator. Then compare with the end of line, as we said before in the previous example. So if we didn't reach the end of line, that means we'll go again, add 1 to the index register. Then we increment it. So we incremented by 1. So the previous value for the index was 0. Now it's 1. Then we ask the user to input a character. This character is going to be stored, the ASCII of that character is going to be stored into the accumulator. Then go to the new location, which is calculated based on the address A. Uh, like as we said, it was 100 plus the new value of index, which is 1 now. So the new address is 101. Go to the next location, which is 101, and store the value that have been stored in the accumulator. Then compare to the end of line again and again till the sequence of characters have been input by the user. Relative, absolute, and symbolic addressing. Here we're going to talk about the relative addresses in this slide. It means simply that we have a base address which is stored in a base register, and once we load the program to the memory, the first instruction is going to be stored in that base address, and starting from that address, the subsequent instructions can be stored using that base address plus an offset. For example, here we have that code, which is sto store the content of accumulator into the memory location, but here we provide the address based on for that memory location based on the address stored in the base address in the base register plus an offset of 10. So if the base register is 100, so we're gonna start storing the value from that code into the memory location 110, because this one is 100 and plus 10, that means this is the offset, and it means go to 110 in the memory and store that value. Okay, now let's talk about the absolute addressing. Absolute addressing means actually that we store the code of the instruction into a specific memory location. So we refer directly to a memory location, like this memory location, which is 32,435. The problem of using this kind of addressing is that if you try to modify the program later on, or if you try to find the bugs, track down a bug, it would be very difficult to go through the program and look at all of these numbers everywhere in your program. Another problem is that if this memory location actually is occupied by and it's not which means it's not free, it has some data inside it. So when you try to load that program or your program into the memory, it might be being used by another program, so it might not be available. Let's look at these codes here, LGA, and this is how it looks like when you write the memory address directly after the operand. So it means load the content of the memory location, this location, into the accumulator. The same for this one, add the content of that location to the content of the accumulator. And the other one is STO, which means store the accumulator data into that memory location. Another type of addressing is using the symbolic addressing. Instead of using absolute address, like what we explained in the previous slide, to go directly to a specific location in the memory, and sometimes it would be difficult to load that program into that location because it might be used by another program. It might not be available, or because of the problem of debugging, you will find a lot of numbers everywhere in the program. So instead of all of this, we use symbolic address, which makes it easier for you to locate the errors or to find the specific memory location in your program. or to refer to a memory location. Let's have a look at this. LDA pay. So instead of typing here directly the memory address, we just type pay, which is a symbolic address. Like consider it as a variable name. Add bonus, the same idea. STO total, that means stored in that location, which is called a total, the value that is being stored into the accumulator. Uh, this one is a lot easier to be read than that one that used absolute addressing in the previous slide. But also noted that the locations where the actual data can be found are not defined in the program itself. If you need to know actually the actual location in the memory where the data stored, it's not defined here. Linkers and loaders. Before your assembly code runs on the computer, it should be translated using an assembler to the machine code. And one of the jobs of the assembler is to create a symbol table. In this symbol table, it will store all the symbols that you have used in your program, the symbolic addresses is going to be stored in the symbol tables. And when you run your program, when you run the code that have been translated, you have two other programs called linkers and loaders that will try to find free memory locations, memory addresses, and store these memory locations or assign these memory locations to the symbols in the symbol table. So that means each symbol in your table would be assigned a memory address. And this process is done by the linkers and the loaders. Whenever you run the program, this is going to happen by the linkers and the loaders. That means these memory addresses that have been assigned by the linkers and the loaders to your symbols in the symbol table is going to be changed every time. That means it's not static. It's going to be changed every time you run the program according to the free memory addresses in your memory. So that means when you run your program, each time a symbol is used, the program jumps to the symbol table to look for the correct address to use.